So looking at question 1 in the review, we're asked to differentiate this equation. Our best bet is to use implicit differentiation. So, and that's because it's not solved for y in terms of x. So I'm going to take the derivative of x with respect to x, that's going to become a 1. The derivative of y with respect to x would be dy dx. The derivative of 3y squared with respect to x would be 6y dy dx. The derivative of 4y cubed with respect to x would be 12y squared dy dx. You'll notice that we have a common dy dx, which you can factor out, which would give us a 1 plus 6y plus 12y squared as the other factor. And then when we solve, we would divide both sides by the 1 plus 6y plus 12y squared, in which case we get 1 over 1 plus 6y plus 12y squared is equal to dy dx. All right, so let's see. That looks like it's, oh, okay. C. I wish I was being dramatic. I didn't see it at first. All right, number 2, we're taking the derivative of an exponential function, d dx of some function e to the u, or in the form of e to the u, is e to the u times du dx, or u prime, either way. Regardless, it's the derivative of whatever the exponent is. So if I'm looking for the derivative of e to the x squared minus 3x, that's going to treat this expression as my u. So I would write it as e to the x squared minus 3x times the derivative of that u, which would be 2x minus 3. All right, so the one that has a 2x minus 3 multiplied by e to the x squared minus 3x would be, it looks like choice D. For number 3, the derivative of a natural log. Oops. So I'm just desperate to write the letter u, I guess. ln of u, finally, it's appropriately written, 1 over u times du dx, or u prime, over u. Because again, this is thought of as the, which gives us a u prime as du dx. So I'm going to look at this as d dx. We have a negative ln, but I'm just going to hang on to that negative. We'll just save that for later. We could apply a rule for logarithms, you know, the power rule, but there's no reason to think it's going to save us any time or effort at this point. So we're going to pop this in, and hopefully we won't live to regret it. Or, well, living to regret something, it has such a connotation to it. So, well, just strike that from the record. Anyway, so this would be my u. If I'm going to take the derivative of the u, it would be 1/2 x squared plus 1 to the negative 1/2 times 2x, and then I'd have a minus 1 off at the end. All right, now I'm going to clean this up just a little bit, just because, I mean, it's already a pretty hideous mess. So I'm going to take the 2's, cancel them, and this would become x over x squared plus 1 to the 1/2 minus a 1. All right, so that's just the u prime. I'm sorry, I forgot the prime. That's the u prime. Now for the actual derivative, it's going to be this whole expression All right, so this whole expression here divided by the original u, quote unquote u, which I'm going to write as x squared plus 1 to the 1/2 minus x. All right, so it looks like our best bet here, I mean, we got to get this to match up with one of those. So we have to simplify a little bit. I think our best bet is to multiply through with a common denominator, in this case x squared plus 1 to the 1/2. So top and bottom multiply by that. So we'd be looking at x minus x squared plus 1 to the 1/2 over, now on the bottom, a little distributive property. So x squared plus 1, because any radical multiplied by itself just cancels to the radicand, minus, poor quality plus 1, by the way, let's fix that, plus 1 minus x times x squared plus 1 to the 1/2. All right, so now I'm looking at this and comparing it to those four choices, and it's still not pretty. All right, but I mean, we got a couple of different ways we can go here. One would be to actually start comparing graphs of my derivative function to the to what we just came up with here. Another thing that we could do is to try to rationalize the denominator, all right, or at least rationalize the fraction in some capacity, all right, because we're raised to a power of 1/2. So what we can do is multiply everything by x squared plus 1 to the 1/2. But what that's going to do is it's going to take what we, well, it's kind of weird. It's going to get rid of the radical here, but it's going to introduce a radical here. All right, it'll get rid of the radical here, but it'll introduce radicals over here. So it's really just a question of whether we're willing to go down that road. All right, so that is the choice. Now, another possibility would be to multiply by conjugates. All right. Now, there is something else that we could do, but it requires us to backtrack a little bit. All right. So if we just get the common denominator for the numerator here, just focus on the numerator, leave the denominator alone, then what we would have gotten is, and I'll just kind of shoot it off over here, x times, well, it's x over because that already has the denominator, x squared plus 1 to the 1/2 minus x squared plus 1 to the 1/2 over x squared plus 1 to the 1/2. Sorry, I lost the 1 there. All right, so that would become x minus x squared plus 1 to the 1/2 all over, x squared plus 1 to the 1/2. With the denominator staying the same, you'll notice that the numerator of the numerator is the exact opposite of the denominator. All right, so that's actually kind of a nice thing, but it's one of those, I don't know, maybe you figure that out before you try something else, but I kind of had to run into a brick wall here before I realized it. But by recognizing that fact, we're able to say, okay, this is over a 1, keep, change, flip if you want, but the numerators in a complex fraction can be simplified against one another, and same thing with the denominators. Bottom line is this would cancel against this to give a result of -1, and we get our simplified form of -1 over x squared plus 1 to the 1/2, which would be one of those. Somewhere. Oh, actually it wouldn't be, because here it is, staring me right in the face. Negative leading coefficient. We then have to correct for this because I said earlier on we need to hang on to that negative. So I got to multiply by a -1, and then that would give me 1 over x squared plus 1 to the 1/2, which is one of the choices. It just doesn't look like it. It's actually equivalent to choice A. Okay, so number 4, a long rectangular sheet of metal, 36 centimeters wide, is to be made into a gutter by turning up two sides of the same length at right angles to the sheet. All right, so let me draw the sheet. All right, and we're going to have two sides that are folded up. All right, now how many centimeters should be turned up in order to give the gutter its maximum capacity? So if we fold this up, what's going to happen is, and we just kind of look down long ways, we'd have sort of a U-shaped, square U, if you will. All right, and it'd have some kind of depth to it. Now we don't know how long the sheet is, so we have to kind of work around that. But we do know some other pieces of information. All right. Oh, actually, it would be open-topped. It just looks kind of incomplete that way. So let me just do sort of a kinda. All right, not what I had in mind. All right, a little bit better. All right, so we don't know what this length is. We do know that this whole side here is going to be 36 centimeters. We have some unknown distance x that we're taking off of each one. Not really taken off, but it's representing the amount that's being removed from the length of the base here and becoming the height once it gets folded up. All right, but we don't know the length of the figure overall. All right, so we can call that something else. We can call that y. All right, so there's two ways to think about this. One way would be figure out the optimum area of this little facet here, so the front piece. So if we were to look at a little cross section, all right, so just focusing on just the front little sliver, just that part. If we were to optimize that area and then multiply it by y to represent the fact that that area could have y distance in that whatever that direction is, then that would get the job done. The other possibility is to write a volume formula incorporating the y, but then you'd have to differentiate around the y, which is completely unknown. So what I think we should do is find the area of a cross section. Fortunately, that cross section is rectangular, base times height, length times width. So 36 minus 2x times the height which would be 36x minus 2x squared, so a of x, a prime of x would be 36 minus 4x. Now, we're looking at optimization, which would be the instance where we would look for relative extrema. We don't have any bounds here that were indicated, although we could use some common sense to figure out that, well, x can't be 0 or less, otherwise there would be no fold to it, and it can't be more than a certain amount. But for now, we're just kind of look for the relative extrema. So 0 would be equal to 36 minus 4x. There's no reason why we would set it equal to 1 over 0, because there's no way for a polynomial function to be undefined. And so therefore x would be equal to 9 as a critical value. All right, so I would test this in a sign chart, going from 0 to 9, stopping at 9, and then going from 9 to something large, reasonably large. I'll say, I guess, 36. But even 36 wouldn't make sense, because if we're taking 2 of those x's off, then 36 would be way more than is possible. So let's say 9 to 18. All right, even that is unrealistic, but got to put something there. All right, now, just using, I'll call it common sense, looking, but it's really graph sense, looking at my original function here for area, it's a negative quadratic, so it's a downward facing quadratic. We know that a downward facing quadratic increases followed by decreasing. So positive, negative, indicating a relative maximum, which is what we're looking for. All right. So maximum capacity would be 9 centimeters. 9 centimeters Let me just frame this the right way, because the maximum capacity is not 9 centimeters. It's when x is equal to 9 centimeters. All right, the maximum capacity itself, it doesn't really ask us for that, but it would be the area multiplied by the length. So we'd be looking at volume v of x, y, would be equal to a of x times whatever the y value is, which in turn would be 36x minus 2x squared times whatever the y value is. All right, and since y is allowed to be variable, that would amount to another component, right? But if we treat it as some constant, then we'll allow it to be a multiplier. But we got to allow for it to go either way with that. So this is one way that we could express our maximum capacity, right? But they asked for the x value that leads to the maximum capacity. So this is what they're asking for in the problem. All right. Number 5, balloon rises vertically at the rate of 15 feet per second. So that's a vertical rate of change. So that's a dy dt. A person watches the balloon ascend from a point on the ground 90 feet away from the spot below the rising balloon. That sounds like an x value, horizontal distance. At what rate? Radians per second. Right? That sounds like a d theta dt. Is the observer's eye rotating upward to follow the balloon when the balloon is 30 feet above sea level? Above the level of the observer's eye. Right? So that's a measure of height, or a vertical distance, so we'll call that y. Right? So we're looking at something that kind of, I would imagine, is along these lines, where you'd have the eye over here. I am incapable of drawing an eye. So that's a scary looking eye, but that's the idea. All right, we got a balloon. All right, that's an attempt at a balloon. Forms a right angle with the ground, or at least the vertical does. Here's y, here's x, here's theta. An equation that would relate all of these different variables. Looks like tangent of theta would be equal to y over x. All right. It looks like the x value is not changing. That person's eye is not moving horizontally. It's actually not moving vertically either, but the distance of the balloon is, right? So the horizontal distance between the eyeball and the balloon is not changing. So I could think of this as tangent theta is equal to 1 over x, where x is a constant multiplier, times y. All right. Differentiating this, I'd get secant squared theta d theta dt is equal to 1 over x, because x is treated as constant here, times the derivative of y with respect to time, dy dt. All right. So I can start making my substitutions, but secant of theta is hypotenuse over adjacent. All right, so secant squared theta would be hypotenuse squared over adjacent squared. All right. So I need the hypotenuse. Now they're telling us to look at this from a point on the ground, 90 feet away from the spot. It's going to be 30 feet above ground level. So I could use that information to determine the value of the hypotenuse. So 90 squared plus 30 squared. So the square root of 9,000. It's not going to be clean as a decimal, but we could simplify it, right? Because 90 times 100 is 9,000. But we could also look at it as 9 times 100. Oh, let's do it this way. 9 times 100 times 10. That'll get us to 9,000. The square root of which would be 3 times 10, which would be 30 radical 10. All right? So 30 radical 10 would be my hypotenuse. But ultimately, I need to square that anyway, which gets us back to a 9,000 no matter how you slice it. So one way or the other. Then on the bottom, adjacent squared. Adjacent is 90 squared, which is 81. 9 times 9 is 81. Tack on a couple of zeros. All right, this could simplify. All right, knock off the zeros. Both the top and bottom number are divisible by 9, so 10/9. All right, so I'd be looking at this becoming 10 over 9 times d theta dt. And honestly, I mean, worst case scenario, just put it all into Desmos. It's like you got the square root of 9,000 squared over 90 squared. And just math bracket, and you'll get it anyway. All right, math bracket, I'm using TI language. So 1 over 90 times dy dt, which they said is 15. All right, so 15 goes into 96 times. So 10/9 times d theta dt would be equal to 1/6. Then a little cross multiplying here. So we'd look at 9 over 60 d theta dt is equal to that, which simplifies a little bit more. Top and bottom divisible by 3. So 3 over 20, and this is radians per second. Right, so one little step of differentiation, but after that it's all just computation. critical numbers. To find critical numbers, we take the derivative. I'm going to rewrite it. F of x is equal to x, parentheses 2x plus 1 to the 1/2. Take the derivative, and then set that derivative equal to 0 and 1 over 0. Now, this is the product between two functions. So I'm going to be looking at my first function, which is x, multiplied by the derivative of the second. So first times the derivative of the second, which would be 1/2 2x plus 1 to the negative 1/2 times the derivative of the inner function, which is a 2, plus the second function, 2x plus 1 to the 1/2 times the derivative of the first, which amounts to just a 1. All right. Now, what I'd have to do is take this and set it equal to 0 and 1 over 0, but for the sake of cleanliness, I'm going to clean it up a little bit first. I got the 2's canceling. X would then be over 2x plus 1 to the 1/2 power, plus another 2x plus 1 to the 1/2. Get a little common denominator action going on here. So that 2x plus 1 to the 1/2, I can think of that as over 1, and then multiply by 2x plus 1 to the 1/2, top and bottom. All right, so a radical multiplied by itself cleans up nicely. So we'd be looking at x plus 2x plus 1, or quality plus, over 2x plus 1 to the 1/2. So that's my f prime of x. All right. I do want to take note of the domain of the original function. Under a radical, you can't have a negative. So I want 2x plus 1 to be greater than or equal to 0. It can be equal to 0, just can't be negative. If it were in the bottom of a fraction, it wouldn't be able to be 0 also. But that's saying if I subtract a 1 divided by 2, I need x to be greater than or equal to a negative 1/2. All right, so, if that helps you eliminate any possible choices, that's great, but it doesn't look like it does that. All right, so this simplifies just a smidge more to 3x plus 1 over our common denominator, 2x plus 1 to the 1/2. So I'm going to take this fraction, set it equal to 0. And I'm going to set it equal to 1 over 0. When I set it equal to 0, I get 3x plus 1 is equal to 0, giving me x is equal to a negative 1/3. When I set it equal to 1 over 0, I get 2x plus 1 to the 1/2 is equal to 0, which means 2x plus 1 is equal to 0. So I can solve by subtracting, and I get x is equal to negative 1/2. All right, so that looks like it's choice D. Now, if you're unsure, take your original function, pop it into Desmos or whatever graphing calculator, f of x. And even if you are sure, who doesn't want to check their work, So x radical 2x plus 1. All right, that's pretty funky looking. But for a critical value, I'm looking for any instance in which the derivative would be undefined or equal to 0, but the original function, I'm really looking for turning points more than anything else. All right, so I got one there at negative 1/3. Now it's just a question of what's happening at negative 1/2. Well, here's negative 1/2. I mean, it looks like that does go undefined. I mean, the original function exists at that location, but if I had to guess, it looks like that that derivative is going undefined, as in it seems to be going vertical there. All right, so And so pretty safe bet that these values are okay. Nothing interesting going on at 0 other than we have an x-intercept. All right, so it doesn't look like we have a turning point or any kind of discontinuity. So any of the choices that involve 0, I would dismiss. All right. So number 7, looking for a minimum point. So I take my derivative, f prime of x, using my exponential e rules. So d dx e to the u is equal to e to the u times u prime, or du dx. So e to the x squared minus 2x times 2x minus 2. Set that equal to 0, set that equal to 1 over 0 for our critical values. And by now we know that, I'm treating even the multiple choice questions as if they're free response questions, because you never know on the actual test. All right. So when we cross multiply and solve, this one, or the one on the right here, becomes irrelevant. There's no instance in which it would be undefined. When you cross multiply, that gets borne out. Grammar. So that's one thing, one less thing to worry about. E to the x squared minus 2x equal to 0, 0 product property. 2x minus 2 is equal to 0. E is a positive number. If you raise a positive number to any power, as long as that power exists, there will be no instance in which we could ever get a 0 as a result. All right, so this one doesn't give us a solution either. The only value that we get that's meaningful would be this one, which would be x equals 1. It looks like there's only one choice with that, but why not give it a look and make double sure? So in my original function, f of x, I would replace the x with a 1 to see what the corresponding value of y is. We get e to the 1 minus 2, which is negative 1, which is the same as 1 over e, which does check out. So we're in good shape there. Number 8 is a Newton's method question. All right, so for Newton's method, it's a very particular approach related to a formula. So, and that formula relies on a derivative. All right, so we're going to have to find the derivative of the original function and incorporate that into the solution. All right, so that's what we're going to do here. So starting off with f of x equals x cubed plus 5x plus 1. I'm going to find the derivative of that. And, it's fairly simple. I mean, in this case, it's just simple power rule. So I'm not really overly concerned in terms of the difficulty level for this one. But when it comes to situations in which you have more complicated functions that make up your question, I guess, then you got to be mindful that, just because this one's power rule doesn't mean that they're all going to be simple. But anyway, this one is nice and easy. 3x squared plus 5. All right. So the general rule for Newton's method is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. All right. So f of x sub n is really just taking all of my entries in f of x and replacing them, or my variables anyway, with an x sub n. So x sub n cubed plus 5x sub n plus 1 f prime of x sub n is equal to 3 x sub n, actually I can just do it without the parentheses, squared plus 5, and then we just build a function out of that. All right, so this recursive function, which calls on a previous computation, is just going to be x sub n plus 1 is equal to x sub n minus this divided by this. So we're just looking for the choice that resembles that. It almost looked like the first one, but it's missing the x sub n. And it looks like it's the second one. Yeah, choice B. All right, so, I mean, if you're looking for a shortcut, it's really just take the derivatives, replace all your x's with x sub n's, and just plug it into a formula. As we learned in class, it's more interesting, or more, well, definitely more interesting, but definitely more complicated when you have to do it, when you actually have to get a solution using Newton's method. All right, differentials. So differentials requires us to determine a function that we can use to approximate this value. So we talked about this in class, where when you're given something like the square root of 3.4, we want to think of that as the result of some function being evaluated. All right? If that were the case, then the function that was evaluated prior to arriving at this expression must have been, or could have been really, f of x is equal to the square root of x. All right? So what we do is we choose a nice value near this number, all right, the 3.4, and we let that be equal to the a value. All right, a nice value related to a square root near 3.4 would be 4. All right, now a differential is really saying take the, well, we're going to find the derivative, but we need to determine what the difference is between our nice number and the given value. All right, so the dx is going to be the difference between those two numbers. All right, so 4 minus 3.4, or 3.4 minus 4, either way, we're going to find the absolute of that anyway, which is going to be 0.6. All right, so the difference between the number that we have and the number that we want. All right, so if we're going to approximate, what we're going to do is find the derivative f prime of x is equal to 1/2 x to the negative 1/2. All right. Now, that's where things get a little weird, because I have a dx here and I don't see a dx over here. But this could be thought of as dy over dx. And I'm going to rewrite this as 1 over 2 radical x. So dy would be 1 over 2 radical x multiplied by dx. All right, so that's the differential form. So this is the differential equation, dy over dx. This is the differential form of that differential equation. All right, so now we get into some substitutions, because we can plug in our nice number evaluated would be 1 over 2 radical 4 times the 0.6. All right, now that 0.6, just for the sake of being able to do this reasonably easily, that 0.6 is the same as 3/10, which is the same as 3/5. So we'd have 1/4 times 3/5, which would be 3/20. All right. Now, what that is certainly not the square root of 3.4. Square root of 3.4 should be somewhere in the neighborhood of 2. What that is the corresponding change based off of the function related to the dx value, that infinitesimal change in x, which really isn't that infinitesimal, but the change in x that leads to a certain change in y at x equals 4. All right. So what we look at is what we have as the square root of 4, right, or a nice value. If I evaluated my original function, f of x is equal to the square root of x. If I evaluated at the a value of 4, I would get 2. All right. Since 3.4 is less than 4, we subtract 3/20 from the square root of 4. All right. So my approximation would be 2 minus 3 over 20. So then I would look at my choices and see which one most closely approximates itself or appears to be the same as 2 minus 3/20, and that would be choice A, which is 1.85. All right. Now, if I had to guess what is the square root of 3.4, I'm definitely not guessing 1.85, but I would know that it's something not too much below a 2. All right. The problem is all 4 of these choices are not too much below a 2, but we could also have a quick look at what the actual square root of 3.4 is. 1.844 approximately, which is really, really bad. Bad? I don't know. Depends on perspective, but you can see how just the square root of 3.4 is one of the choices that's designed for you to, like if you don't know what a differential is, that's designed for you to get tricked and take that one. But that would be, I look at it as, all right, so don't choose that one because that one can't be the right answer. So at least if you had to guess, you're down to a 1 in 3 chance. And odds are, if I were to guess on something like this, I'd be like, all right, well, the calculator says the square root of 3.4 is 1.844. I'm going to choose something that's not that, but close to it. And the closest one to that is 1.85. Right? So it's more of a strategic, educated guess, but even more strategic than that. All right. Local linearization, still with the theme of a nice number approach. So nice numbers for logs, specifically natural logs. We're talking 1, e, and if need be, powers of e. All right. So I'm looking at this and saying, all right, if I can get what's in this expression here to be a nice number, that would be really good. All right. So a nice number, like I said, would be like a 1. Well, if x is equal to 3, then that would actually make the natural log really nice. It would be ln of 1. That's beautiful. All right. So f of that nice number, f of 3, that's my way of asking you to verify that it truly is a nice number. 3 times 3 times ln of 3 minus 2. 3 minus 2 is 1. Natural log of 1 is 0. 0 times anything is 0. Yep, 3 is a nice number. All right. F prime of x. Well, our original function is 3x ln, so it's going to involve some product rule. I'll rewrite f of x here and exaggerate the product here. Ln of x minus 2. We have our first function, first times the derivative of the second, derivative of the natural log, 1 over whatever's contained within the natural log times the derivative of whatever's contained within the natural log, which happens to be a 1, so we're good to go. Plus my second, ln of x minus 2 times the derivative of the first function, which is just a nice clean 3. All right, so I got to put that into the field here, so let me just clean it up a smidgy. Not really a whole heck of a lot of housekeeping to do here, but I would write this as 3x divided by x minus 2 plus 3 ln x minus 2. All right. Just parentheses where appropriate. Whenever you have a fraction, you generally want to put the parentheses around the top and the bottom separately. Now, f prime of a, all right, the convenient or the nice a value, 3 times 3 times 1 over 3 minus 2. Well, 3 minus 2 is 1, so that's irrelevant. So we get a 9 for this part, plus ln of 3 minus 2 times 3. 3 minus 2 is 1, natural log of 1 is 0, so this goes to 0. So the derivative at that a value is a nice clean 9. All right. So my linearization model, L of x, f prime of a, plus, well, there's different ways to write it. F prime of a, I think I said plus, I meant times x minus a plus f of a. But some folks have it written as f of a plus the f prime of a times x minus a. Either way, it's commutative. All right, but this, writing it this way will match my auto grader, which will make everybody happy, so that's good. All right, so I realize there's a little typo here. I'll have to fix that. So f prime of a, we figured that out as 9 times x minus 3 plus f of a. F of a we determined earlier was equal to 0. So my linearization model, just so it's easier to type into the space, 9x minus 27. All right, so the linearization, this, I apologize for this. This shouldn't be an a, because if we put an a in there, that's could just give a 0. This should be L of 2.98. All right, so you'd get that by plugging in 2.98 for x. So 9 times 2.98 minus 27, which would be negative 0.18. All right, and if we look at our original function, f of x equals 3x times the natural log of x minus 2. All right, so that's my original function. Let me get rid of this stuff. All right, so that's what we're up against there. If I type in f of 2.98, I get something pretty dang close to the negative 0.18. All right, so we're in pretty good shape here.